Okay, Assalamualaikum and hi to all. So this is the fourth video for the BMCG 3723 heat and mass transfer post convection external. So in this video I'm going to explain flow across tube banks. Okay, normally in these tube banks we have a typical arrangement which is inline and staggered, and as I put here, the outer diameter D of the tube is the characteristic length. And as you can see in the figure, there is two figure at the bottom of this slide, which is inline and staggered, and you can see the arrangement of the tube for inline and staggered, so you have the general idea. And for these two cases, the arrangement of the tube are characterized by the three parameter, which is the transverse pitch ST, longitudinal pitch SL, and the diagonal pitch ST. So based on the figure, you can see where is the ST for inline, staggered, and SL for both cases also. And as you can see, the diagonal pitch is only appear in the staggered case, where we can calculate the distance of SD from the theorem Pythagoras. Okay, so I will start with the inline arrangement. Okay, from the first note mentioned here, as the fluid enter the tube bank, the flow area decreases from A1 to AT between the tubes, which is A1 is before we enter the between the two tubes, and AT is exactly at the in between the two tubes. So from here we can see that there is a variation in the surface area, and mentioned here, thus the flow velocity increases. What it means by this is, from the fluid mechanics we know that volume flow rate in and out should be equal. So from this equation, V1 A1 equal to A2 V2. So we can input the area as A1 and AT, and then we replace the A by the equation of ST times L for the surface area at the exactly before the tube, and AT at exactly at the tube, in between the tubes. So from here we know that the surface area at A1 is larger than AT. So from there we can know that the value of V2 is larger than V1 from this correlation. So here I put it V2ST equal to Vmax. And it mentioned in tube banks, the flow characteristic are dominated by the maximum velocity Vmax. So if you want to know the Reynolds number in for this case tube banks, we should use the maximum velocity as it put here. The Reynolds number is defined on the basis of maximum velocity as Reynolds number equal to rho V max D divided by mu. So this is 739 equation for Reynolds number. And then from this correlation also we can rearrange the equation. For inline arrangement, the maximum velocity occurs at the minimum flow area between the tubes, as I put in the equation 740, where the Vmax equal to St divided by St minus T times V. V here is the velocity at A1, and Vmax is the velocity at AT. St is the distance between the two tubes in the vertical direction, and D is the diameter of the tubes. Okay, now we look into the staggered arrangement. Okay, as you can see in this figure, so the red arrow is the flow direction, and the fluid flow is flowing from surface area of A1, it goes to A2, and then it goes to the AD area, which is at in the diagonal area. So for these cases, we have two cases of flow, two cases. For case 1, if the 2AD is larger than AT, then the velocity max occur at AT, here at AT. So we can use the same equation as in inline arrangement for the Vmax, maximum velocity. And then for case 2, if the 2AD is smaller than AT, then Vmax occurs at diagonal cross section, where we can use this another equation as to calculate the maximum velocity. So for these two cases, the summary is as shown in the blue rectangular. For SD larger than ST plus D divided by 2, and for SD smaller than ST plus D divided by 2. So I put a note here. The nature of flow around a tube in the first row resemble flow over a single tube, as I put in the previous video, third video. And the nature of flow around a tube in the second and subsequent rows is very different. So it means that the first row we can assume as the single tube, but when we move to the second flow, second tubes, second arrangement of the tube, so the flow is very different, because the level of turbulence and thus the heat transfer coefficient increase with row numbers. So, and the last point is there is no significant change in turbulence level after the first few row, and thus the heat transfer coefficient remain constant. Okay, we already looked into the parameter for inline and staggered tube banks. So we need to know the Nusselt number throughout these tube and banks. So Zukaukas has proposed correlation whose general form is Nusselt number equal to HT divided by K, as shown in this equation. So the value of C, which is the constant, M power of Reynolds number, and N power of Prandtl number depend on the Reynolds number. And you can calculate the Reynolds number, and you can know the value based on table 7.2, as I shown on your right hand side with the blue rectangular. So I put a note up there, where the for tube banks with number of row is equal to 16 or larger of rows. So you can use this equation directly and Zukaukas equation. But for the cases of the number of rows is less than 16, you need to add a modification. Here it mentioned that the correction factor, which are written in the red color, F, and the value are given in the table 7.3, as I shown on your left hand side, bottom table, table 7.3. So you just need to add the F value in front of the Zukaukas equation, which is known as the correction factor, to calculate the Nusselt number. Okay, so we already know everything for now, which is the inline and staggered parameter, and then we also know the how to calculate the Nusselt number. So here I'm going to show some of the parameter, which is the Tm is the mean arithmetic mean temperature, which is the average of the T1, T inlet plus T exit divided by 2. This is the average of the inlet and outlet temperature of the tube and banks. So all properties should use this arithmetic mean temperature except for PRS at the surface. And then we can calculate the temperature difference throughout the system from the surface temperature to the surrounding temperature. But in these cases, we will over predict the temperature difference. So we need to use the log mean temperature, which is given here, log mean temperature difference. So you need to use ln to calculate the temperature difference. So we also give the exit temperature as mentioned here, TE equal to TS, TS is the surface, minus TS in a bracket, TS minus T initial, T inlet. So with the exponential, AS surface area, H is the convection heat transfer, M dot is the mass flow rate, and CP is the specific heat. And from this all this temperature difference, we can calculate the heat transfer rate, where Q dot equal to HAS delta T ln log mean temperature difference equal to M dot CP T exit minus T inlet for heat transfer rate. Okay, so we already know the inline, staggered, and also the Nusselt number, how to calculate Nusselt number. This is basically the summary of it, which is the how we calculate the Nusselt number from Zukaukas equation. And for the table 7.2, the number of tubes, banks, NL is larger than 16 and above, whereas for 7.3, we should add the correction factor to the Zukaukas equation, as put out here, n equal to f and u, and this is for the cases where the number of tube is less than 16. Another important parameter for flow over tube banks is the pressure drop and also work of pump. So as you can see here, the pressure drop is delta P equal to NL, which is the number of tubes, banks, and then F is the correction factor and X is the correction factor. So we have two new parameter here, which is the friction factor and X, the correction factor, times rho V, maximum velocity of the fluid flowing in the tube banks, divided by 2. So from this equation, you can calculate the pressure drop along with the friction factor. So on your left hand side, we have two friction factors, which is on the top is the inline arrangement and the bottom is the staggered arrangement. So as you can see in the inline arrangement, we have this value where the SL is equal to ST, or the value of PT is equal to PL, where you can see here PL is PL and PT is ST or SL divided by D. So if this value is equal, then the correction factor will be equal to 1, and if it have a different value, then the correction factor will also will be different. So for the cases of staggered arrangement, you can see in the figure, the bottom figure, we have SD is equal to ST. For these cases, the correction factor is equal to 1. For different value, then the correction factor will be different. So from the pressure drop, from the correction factor and friction factor, you can calculate the pressure drop, and then from the pressure drop, you can calculate the work of pump. So you need to consider also the, how to say, if you want to increase the number of tube, you should also consider the power of pump that you need to put into it. Okay, so this is the end for this fourth video, which is for force convection of external. And for your further understanding, you should look into the exercise that will be given in your ULearn. And hope you enjoy this video, and thank you.